Everything we've done so far in the second half of calculus has led us to the concept behind today's lesson, which is why finding area takes us in the backwards direction. And today we're going to connect it to actually going backwards on derivatives as well. And that is the foundation for the biggest theorem in calculus, which is called the fundamental theorem of calculus. So big, in fact, that it has two parts, the first of which we'll be introduced to today. So our learning targets for the day are to use the fundamental theorem of calculus, part 1, to evaluate definite integrals and to determine antiderivatives of basic functions. We're going to add to our growing list of our interpretations of the integral, which we know that this symbol means sum, and when we are approximating the integral from a table of values, it gives us the total amount over time. When we integrate a function when we're given a graph, we find the exact area between the function and the x-axis. And our new interpretation for the day is if we are given the integral of a function, we evaluate it by finding the antiderivative of that function. So I'd like to make the connection between area and antiderivative by looking at the integral of the same function, 2x, over different intervals of time. So you'll see that the graph produces a triangle every time. So let's go ahead and find the area for each one. By using the x and y values for each triangle, I went ahead and calculated the half base height. And when you see those results, I'm hoping that you see quite a special pattern with those numbers. They are in fact the perfect squares. And furthermore, they're the perfect squares of each of the upper limits for the integrals. So let's think about that relationship between, we found the area under the function 2x, and each time it gave us the value of x squared. You might be thinking about the relationship between x squared and 2x. In the first half of calculus, they are related by finding the derivative. So the derivative of x squared gave us 2x. But what we just did by finding the area was we actually produced the antiderivative, or going backwards. So that leads us to the big theorem that I mentioned, the fundamental theorem of calculus, which says that if a function is continuous on a closed interval, then capital F of x is what we use to represent the antiderivative. Some people call that the parent function because it's the big F. Then when you evaluate that integral of f of x from a to b, you do so by finding the antiderivative and evaluating it from your lower to your upper limit by plugging in your upper limit to the antiderivative and then subtracting and plugging in your lower limit to the antiderivative. So now that we know that we need to find antiderivatives, we need to build our skill set for finding derivatives backwards, and that's based on what we already know about going forwards with derivatives. So you might remember one of the first power rules that we learned was the power rule. So that's a good place to start for antiderivatives as well. So we're going to use this chart to remember how the power rule works for the derivative and then dissect it and figure out how to go backwards upon that. Using a general function of a times x to the n, we know that the power of n comes down in front of the coefficient, gets multiplied, and then you subtract 1 from your exponent. So let's go ahead and specify each step that's happening in that process. So we multiply by what we'll call the old exponent, and then we subtract 1 from that exponent. So to go backwards, it should make sense that we're going to do the exact opposite of those things. But we also need to realize that those steps actually have to occur in the opposite order as well. So our step 2 is going to become our step 1, but we're going to do the opposite. And our step 1 is going to become step 2. So what we'll do is we'll reverse the steps here and then talk about what it looks like in our general formula. So step 1 is going to become to add 1 to the exponent. And then step 2 will become dividing by, instead of the old, it becomes the new exponent. So when we look at our general function here, we have ax to the n power, and our first job is to add 1 to that power. And then step 2 says to divide by the new power, which is n plus 1. So that gives us the general formula for the power rule for antiderivatives. Let's use this first example to practice our power rule for antiderivatives and also apply the fundamental theorem. You might have noticed up here that there is a set of square brackets, and that indicates that you are finding the antiderivative, and then you put the lower and upper limit on the right side to say that next you're going to evaluate at those limits. So using the power rule on 3x squared, we keep the 3x, we add 1 to the power, getting to the third power, and then you divide by that new power of 3. We'll do the same thing for the second term, which happens to be 2x to the first. So adding 1 will give us 2x squared, dividing by that new power. And then that 1, it may help you to think about x being to the 0 power, which is not there, but we know it is. So you add 1, giving you x to the first, divide by that new power, which just happens to be 1. So after we simplify, we have x cubed minus x squared plus x. We're going to evaluate that from -1 to 0. And we always start by plugging in our upper limit first. So each time you see that x, you'll put a 0. And then you're going to subtract, because it's f of b minus f of a. And then insert a -1 for each x value. And if you were on free response on the AP exam, you actually could stop here as soon as you find your antiderivative and plug in your limits and subtract them. You do not have to evaluate further. But just to practice for multiple choice, looks like the upper limit plugged in is going to give us a 0 minus, and all of these -1s, when you apply the powers, I believe gives you a -3. So your final answer is +3. There is one exception to the power rule that we need to be aware of, and that is when x is to the negative first power. So let's think about why that would be if I go to apply the power rule for antiderivatives to that x to the -1 power. My steps say to add 1 to the new power, but then attempt to divide by the new power, which is 0. And we learned a long time ago in mathematics that we cannot divide by 0. So that's why it's an exception to the power rule. So if you encounter a function that has an x to the negative first, and it may have a constant added to it, then our antiderivative is going to be the natural log of that x to the first plus c if there is a constant. And now that you see that, that should look familiar because we know if we take the derivative of the natural log, it gives us that 1 over x. So that's the connection. Also, I need to mention we do have to put the absolute value bars there because we may not natural log a negative value, so that keeps us safe from doing so. So if we look at that first example, I recognize right away that it's x to the negative first. So knowing my exception to the power rule, I'm going to say it's the natural log of the absolute value of x. That's my antiderivative, evaluated from 1 to e. So the fundamental theorem says to plug in your upper limit minus your lower limit. And these are two values we're expected to know without a calculator, and we've talked about those this year. The natural log of e is 1, the natural log of 1 is 0, and so our final answer would be 1. One of the nice things about finding antiderivatives is that we're able to check our work, which we weren't able to do so when we were working with derivatives. But if you look at your antiderivative in that first example, you take the derivative of x cubed, it gives you 3x squared. X squared gives you 2x, and x gives you 1. Same with the natural log of x, it would give you 1 over x. So if you feel comfortable, give the other couple examples in each section a try, and then when we come back together as a class, we'll talk about those, as well as look at the trig antiderivatives and antiderivatives